Okay. So we were discussing continuous random variables, and we defined random variable. So let me just recall how we defined random variable. So we have a probability space, and we have a function from probability space to real line. Of course, if you want the if the same condition will hold in a I mean, you have to modify the condition if you want the random variable to take values in complex plane or something else. So here the only is a random variable if this set x less than or equal to small x is strictly for all x. So this is the random variable, and we say it's continuous. X is continuous. The random variable x is continuous if probability of x equals x is 0 for all x. This is equivalent to saying this distribution function which we defined fx is continuous function. So we deal with not just continuous random variable, we deal with random variables, continuous random variable which admits a density. So x admits a density, x admits a density function if this f of x, this distribution function is just f of fx x is equal to probability of x less than or equal to x. And this is given by minus infinity to x, some other f of t dt for some function. Of course, this cannot be arbitrary function. This has to be satisfies some condition, but for our purpose, mostly it will be even continuous. Okay, we will be dealing with continuous function, or maybe finitely many points it may not be continuous. So then examples, we saw some uniform distribution, exponential distribution. So we will see that, I mean, we defined uniform distribution as follows. We can take we can take any interval. We take this interval 0, 1, and then so it is just, you want to define, I mean, you can take, it doesn't matter, because we are going to talk about length. Single point interval doesn't matter. Mostly you can take it like this. Okay, so this is a random variable where x in any interval AB, this, I mean, probability of this is given by b minus a. That's all. Because, I mean, otherwise you have to divide it by something. So this is just b minus a. So the distribution, so the density of, hey, shall I pause for some time? You can finish. Yeah, you go out. Huh? Yeah, let's discuss later. So, okay, you can discuss the assignment later. Yeah. There was some question we can discuss. No, yeah. You have stopped. If you have some question, we can discuss here. Okay, and I shouldn't get diverted. That's all. You can discuss something, but maybe we can discuss together. Okay. So this is that the, I mean, so we have then we know the distribution function. The distribution function. That's okay. This is uniform distribution. You know what is uniform distribution. Then we can get the exponential distribution which we have defined. We can get it from here by defining a function. If x follows uniform distribution in this interval 0, 1, okay, then we define a random variable which is f of x, I mean 1 by lambda minus 1 by lambda log x minus 1. Okay, then this will follow the exponential distribution. Okay, so that f of x is that we want to find the distribution of f of x. So for that we have to find the probability of f of x less than or equal to some small x. Okay, this is equal to log 1 minus this log of this x minus 1, that is, I mean, the minus 1 by lambda log of x minus 1. I'm sorry, 1 minus x. Because x is less than 1, so it should be 1 minus x. 1 minus x is less than or equal to x. Okay. This is equal to, you can take, since there is a minus sign, that will go there, and it is just minus lambda x is less than or equal to log of 1 minus x. Careful. So this is just equal to x is less, again, x will be less than or equal to 1 minus e power minus lambda x. And this is equal to 1 minus, I mean, because it's, I mean, x is less than or equal to 1 minus e power lambda x. And this is the uniform distribution. Okay. This is just precisely equal to the value of that. I mean, x should be great, x will be greater than 0, and x will be between this. So this is just precisely equal to 1 minus e power minus. So if you define, if you have x follows uniform distribution, and f of, I mean, f is given by this function 1 by lambda log 1 minus x, then f of x will follow the exponential distribution. I mean, we can directly compute this. Lambda has to be greater than 0. I mean, that is how we define lambda is greater than 0. And this is for x greater than 0. Okay. For x less than 0, it is 0. Yeah. I mean, this should be less than 1. E power minus lambda x should be less than 1. So we can generalize this. We can have a general theorem. We can have more general theorem, but this is something easy to prove. So that's what we will use it. There's a more general theorem for change of variable, but we will only prove this, at least for the time being. Okay? So if x is a random, x is a continuous random variable with density f, and we assume that f is, I mean, f is supported in some interval, that is f of t equal to 0 if x is not in some interval I. Some interval, doesn't matter whether it is open or closed or something. So some interval I. Okay. So it is outside this interval, it is 0. That interval can be infinite also. Okay, we just assume this. Then phi is a function from I to R, okay, which will be, of course, T of I. It will be range of phi of I, which is T of I. Is a strictly increasing function. Increasing or strictly decreasing function. Decreasing function. Okay, and it's differentiable. Then phi of x has density f of, see, if you have a increasing, strictly increasing or strictly decreasing function, that is invertible, right? F of x, you can easily verify. F of x is less than y, then f of x is strictly less than y, or strictly less than f of y. Similarly, for the decreasing one, so if it will be 1, 1, and it is on 2 because we are taking only the range. Okay, if the phi inverse is from, I mean, okay, f of phi inverse, f of phi inverse x times then d of phi inverse by dx. This will be the density. I mean, this is the theorem. Okay? So the inverse x is, and we know that that is differentiable. The inverse is also differentiable. So I mean, you know the formula. You can even find it. Okay? Inverse, this is just if you have dy. This is like dx by dy. If it is dy by dx, I mean, here I have written dx here. This is like okay? I mean, if you have phi, then phi prime is like dy by dx. Phi inverse prime is dx by dy kind of thing. I mean, this is just you have to take the inverse. That will also be invertible. That will also be differentiable. Okay. So that's all. The proof is, I mean, to find this, actually, the proof is you can just differentiate it and get the answer. Actually, this should be mod. Sorry. Yeah, there should be a mod here. This is the answer. I mean, if x has density f, then phi of x has density f of phi inverse x d phi inverse by the derivative mod of the derivative. Okay? So you can prove you can find this answer by differentiating, but that's not the proof. For the proof, you have to, because this original f may not be, the distribution function. With this, we don't assume anything about this function. Okay. So for that, you have to kind of, you can integrate it and get the answer. Okay? So let's first differentiate it. So we want to find so we have our original function f of x. Fx is the distribution. F of x is equal to minus infinity x f of t dt. This is the original distribution of this. Now we want to find this p of x less than or equal to x, maybe y or something. That's what we want to find. See? Okay. And this is just equal to, of course, this is equal to p of x less than or equal to phi inverse y. If, there are two cases, of course. So let's assume that phi is increasing. Let phi be increasing. Or let me write for decreasing. The increasing will be easy. Okay. Increasing is direct. So I will write it for decreasing. I don't want to do both of them. So let phi be decreasing. Then we want to find this p of x less than or equal to y, which is equal to p of x. The inequality will be reversed. So x is greater than or equal to phi inverse y. So this is the inequality. And that is equal to 1 minus f of phi inverse y. Okay. Right? Okay. This greater than or equal to greater than doesn't matter. Okay. This will be supposed to be greater than, strictly greater than, but because it's continuous, it doesn't matter. Okay. Now by differentiating, you will get the answer. Now if you differentiate it, so this is equal to f. So now, we want to find the density, then the density, this is x of this. Then if you want this is what is the distribution of phi of x. Now, if you differentiate it, you get the density. That is just to get the answer. Then you can prove it by, so let me just, so if you differentiate it, what happens? If you differentiate it, so that is called f phi of x, y. If you differentiate it, that is equal to, you will get a minus sign here, and you will get f of phi inverse y times d phi inverse by dy. But then this is negative. This is, since phi inverse is decreasing, this is negative. So this is equal to f of phi inverse y mod of d phi inverse by dy. Okay. On the other hand, if you have your phi is increasing, then it will be positive, and you will get the minus sign will not be there. So this is for the decreasing case. So if you want to prove it, for proving you assume, you take this function, you integrate it from between 0 to x, and you should get that the distribution of phi of x. That's what you should get. So to prove it, so let us take this function. Let's take this function, which is z of x, z of y equal to f of phi inverse y mod of d phi inverse by dy. Okay. Which one here? This is x, correct. Yeah, that is original x. You are right. Okay, now you want to find, so we want to prove that this is actually the distribution. This is actually the distribution of like this. Then let's compute this 0 to x, sorry, minus infinity to x of this function, which is f of phi inverse y. Mod of this is going to be minus of that. Okay? I'm assuming phi is decreasing. Okay, I'm still assuming phi is decreasing. dy. Okay. Now, if you just substitute phi inverse equal to, I mean, if you substitute, let z is equal to, is x is equal to phi inverse y, then this will become x. So this will come. I should have used different thing, but anyway, it's okay. So this will become phi inverse maybe z. Okay. Then this will become phi inverse of x, and I mean this will become phi inverse of, actually this will be between phi inverse. I mean this will be between phi inverse phi of d to this, right? See, I suppose, I mean if I is equal to ab, okay, then phi of I will be phi of a, phi of b, right? Sorry, phi of I will be phi of b, phi of a, because it's decreasing. Okay, so this will be from minus infinity, it will start from phi of b only. Okay, so this will be, so this will become between b to b to this, b to this of, okay, this is right, then f of z dz. Okay, that's what we get. Yeah.
Like a different pi.
Yeah, this phi. This is equal to, no, this is a different phi. This not this. Maybe, okay, this is okay. I mean, I haven't used it, I have directly written it. Okay. Okay. Yeah. No, I just take, I mean, you understand the idea, no? I just take this function and integrate it between minus infinity to x. That is same as integrating between phi of b to x. So change of variable, it will be to this. Okay. Now this is equal to, I mean, we know that this is a to b of this f. This is f of this. Okay. A to b of f of x, f of t dt, whatever, is 1, right? Right. So because of that, this will follow. So you just subtract, I mean, you just subtract it and take it. Integral a to b f of z dz minus a to b f of z dz. Then this integral b to p inverse x f of z dz. And finally, we will just get 1 minus, this is 1, of course, 1 minus, when you subtract this, you will just get, I mean, there will be a minus sign somewhere? No. Huh? Did I? No, there is a minus here. No, there is a minus here. So this should be minus, right? Minus. So this will become P inverse x to B. It will reverse. So you will just get from A to P inverse x. Is okay? And this is precisely 1 minus f of P inverse x. Yeah, that's what we want. I mean, I'm just writing it. It's very easy. I mean, if you think about it, it's very clear. But I'm just writing it in detail. I think everything is clear. Okay. Huh?
Not just differentiate this.
See, for that, differentiate what? If you differentiate, f may not be differentiable. So as I said, when you want to find the answer, you differentiate it and find the answer. But the proof justification is by integrating. Okay, but you can just differentiate and find the answer. That's okay. But then to prove that that is actually the density, you have to integrate it and show. Because the original, I mean, there may be some. I mean, this is a theorem in general. Okay. So for that, you need to integrate it and show. I mean, this will be most of the time it will work. You need not worry about it. But I'm over once in a while we have to check it. Okay. This is okay. So this is the proof of it. Okay. So you can apply to many things. For example, I mean, let's see some example later. So now we will. So now I mean, I want to get some one distribution from another distribution. This is an example. Okay. Let x follows uniform in minus pi by 2 to plus pi by 2. So uniform distribution. Okay. That is x in some interval I, where I is contained in this pi by 2 minus pi by 2 plus pi by 2. And that is equal to, if I is AB, what r theta 1, theta 2, because it's angle, theta 1, theta 2. This is theta 2 minus theta 1 by pi. Okay. This is the probability of this. Probability of x in this interval. I mean, I'm saying x follows uniform minus pi by 2 to pi by 2. That means probability of x in this interval, theta 1, theta 2 is this. Because I'm going to use the function tan theta, so that's why I'm using it. I mean, I'm a tan function, so that's why I'm using theta and other things. Okay. Okay. Then you want to find the distribution of tan x. Okay. Find the density. Okay. Density of tan x. So what is the density of this uniform distribution? Density of x, which is fx, at t is equal to, then what is the distribution? It is just 1 by pi. 1 by pi for all t. For all t in this interval, minus pi by 2 to pi by 2. Okay. And equal to 0 otherwise. Okay. In this interval, it is just constant function. Okay. Now you have tan x. You just have to apply that formula. Okay. Tan is an increasing function from minus pi by 2 to pi by 2. It starts from minus infinity, it goes to infinity. Okay. Then the distribution, then the density of tan x. Okay. If you use that formula, you just have to differentiate. I mean, the density is 1 by pi. So if you apply phi inverse or something, it's going to remain 1 by pi. You have to just differentiate tan inverse x. So that will be 1 by 1 plus x square, right? This is the derivative of tan x, right? Tan inverse x. Okay. So you got this. So this is the density of tan x. If x follows uniform in minus pi by 2 to pi by 2, then tan x will follow this. We just applied this formula and we got it. Okay. And this distribution is what is called Cauchy distribution. Okay. So before talking about normal distribution, when I introduced normal distribution in the last class, so before talking about that, we will prove something about symmetric. What we will define what is called symmetric distribution, and we will prove some equivalent condition for that. So there are two. I mean, symmetric distribution. Symmetric can be defined more generally, but we will talk about only this symmetric distribution around 0. If you shift it, it can be symmetric about any point. A random variable or a density, a density function f is symmetric around some point mu in R if f of mu minus x is equal to f of mu plus x. Okay. In particular, I mean, this we say just symmetric or something. In symmetric, f is symmetric. When we say f is symmetric around 0, this we call it just symmetric. If you say just symmetric, it's symmetric around 0. If f of minus x equal to f of, okay, then the proposition is the following. I mean, density function satisfies this. Okay, this is for symmetry. I mean, this is the function is even function. That's all. Okay, f of minus x equal to f of x. Okay. This is symmetric around some point, which is usually the mean of that random variable. So the proposition is f is So I mean, and then more definition. A random variable x is symmetric if x and minus x have same distribution. This is the definition of symmetricity for random variable. Okay? A random variable x is symmetric. By this we mean symmetric around 0. Okay? When I say just symmetric, it's symmetric around 0. Symmetric if and only if f is the density function. I mean, this is for a continuous random variable with this with density. That's what we are discussing. Okay, if the density is, this is true in general also. You can talk about. I mean, you can talk about the mass function and do that for discrete random variable also. But this is I mean, that's our same proof will work. We are using integration. You have to use sum. Okay, which is more easy. The random variable x is symmetric if and only if the density is symmetric. Okay, this is the theorem. This is the proposition. Density is symmetric. By the time I mean it's symmetric around 0. If it is an odd even function. Okay? Random variable is symmetric if x and minus x have the same distribution. These two statements are equivalent. That's what this says. A proof. Okay. Okay. So suppose f of x equal to f of minus x, that the density is symmetric. Okay. Then we want to prove the random variable have the same distribution. So for that we have to find x less than or equal to x should be equal to minus x less than or equal to x, right? That's what we want to prove. That's what it means by saying that they have the same distribution. So this is equal to minus infinity x f of t dt by definition. Then this is equal to integral minus infinity to x f of minus t dt. Right? Minus t dt. So if you substitute minus will go here. I mean, this is a really easy thing. Minus will go here, and then you can take the. I mean, this will become minus x. The change of variable, you substitute minus t equal to something, then this will become minus x, and this will go down, and the whole thing will become. This is equal to minus x to infinity, right? Minus x to infinity f of t dt, right? Okay. And this is equivalent to, this is same as saying probability of x greater than or equal to minus x. It's right? Yeah, x greater than or equal to minus x. And that is equal to probability of x minus x less than or equal to x, which is, this is what we want to prove. Probability of x less than or equal to x is same as probability of minus x less than or equal to x. Okay. This thing implies fx is equal to f minus x. There is nothing I have done. You take, this is the distribution of plus x. By definition, it is this. You use the fact that f of t equal to f of minus t. Use change of variable. You get minus x to infinity. You get this. That means this is x greater than or equal to minus x. That is equal to this. So you get this. Okay. So this is clear. Now we want to prove the other way. I mean, the statement should be something. I mean, see, you may have different density function. You may change it at some point, and you may have different density function. If and only if the density is not correct. If and only if, I mean, it admits a density function which is symmetric. Density function you can change it. Okay, I mean, density function anything which satisfies that integral. Okay, if and only if x has a symmetric density. Symmetric. Yeah. Oh, one second. Yeah. What is the question? Okay. I mean, a random variable is symmetric if and only if X has a symmetric density. There is no the density. I mean, the density is not unique. Okay. So now we want to prove the other way. Suppose we want to prove, suppose Xn minus X has same distribution. Okay. Same distribution, say with density, I mean, with density F. Okay. Same distribution with density F. Then you take G of t equal to F of t plus F of minus t. Okay. We want to, so this is of course a even function. This is symmetric. So we want to prove that this is the density of both F and minus F. Okay. Oh, sorry, X and minus X. Okay. So now we want to integrate it from minus infinity to X, G of t dt, which is equal to half into integral minus infinity to X, F of t dt. This of course gives that we only have to worry about this minus infinity to X, F of minus t dt. We have to worry about this one. Okay. Now we say, so we have to prove, I mean, we only need to prove I mean, this is same as probability of X less than or equal to X. Okay. Half of probability of X less than or equal to X. We have to prove that this is also probability of X less than or equal to X, capital X. Only need to prove that this integral minus infinity to t F of minus t dt is equal to probability of X less than or equal to X. That's what we want to prove. The same idea will work. Minus infinity to t F of minus t dt. You change it, you change minus t here. So this will become minus t and that will come here. You will get a minus sign, but that is cancelled with reversing the integral limit. Minus t to infinity, okay, F of t dt. Okay. And that is equal to probability of, again, probability of X greater than or equal to, sorry, this is minus X, minus X. Yeah, that is same as you can, I mean, you can write X or minus X, it doesn't matter. I write minus X because X and minus X, we are using the fact, I mean, only now we are using X and minus X, they both have the same property. Minus X greater than or equal to this, and that is equal to same as probability of, since minus X also has the same distribution, okay, so you can write minus X here, which is X for X less than X. So this implies this G of t, this is equal to, this whole thing is equal to probability of X less than or equal to X. From that it follows. This is equal to probability of X and S less than or equal to X. This is also, we have proved that this is equal. So here, yeah. Okay. Just change a variable and something. Okay. So this is fine. So examples of symmetric distribution. We want to give two examples. If we have something defined on the positive, if you have a random variable which is defined on some positive real line, then we can extend it to the negative real line and do something. I mean, in some, for example, we take the exponential distribution. So exponential distribution was X is exponential lambda, means that I mean, the density function is given by, I mean, the density is given by lambda times e power minus lambda t, right? For t greater than 0. I mean, the distribution of this is 1 minus e power minus lambda. Lambda, if you have x here, lambda x, okay, for x greater than 0. If you differentiate it, you get that. Okay. So this is the density of that. So we want to extend it to both sides, but then we want to make sure that the whole total probability is 1. So we define a new probability. We define a new random variable, new density function. Okay. I mean, there exists a random variable that FYT is equal to, there is a lambda here, lambda half of lambda into e power minus lambda mod. See, we have to make sure the minus sign is here, and that, I mean, this should be negative so that it will be less than 1 and it integrates to 1 for t now. I mean, you forgot about this is exponential. I'm defining this is double exponential, okay, which is symmetric. I mean, I'm giving example of symmetric density function, okay, which is just f of, I mean, this is what you should think about, worry about. Okay, this is half. I'm using half because we will get if you integrate this, we will get 1 in the positive real line, 1 in the negative real line, and it's the same thing. Okay, I mean, just the sign is changed, and you will get half of. If you have half, so the total probability will be 1. Total integral will be 1. So this is a density function. Okay, this is symmetric, of course. You have mod t and plus or minus d. So the next one is normal distribution, which we have defined. Okay, so this is example 1. Okay. Our example 2 is normal distribution. That is x follows. We define normal for 0, 1. This is, I mean, if we shift the normal, which also I defined the last class, which I will define again. So that will be symmetric around the mean. Here it is around 0. Okay. Then the fx at t equal to e power minus 3 square by 2, 1 by square root 2. Okay. This is also symmetric around 0. This is the normal distribution. Okay. Huh? F of t equal to f of minus t. If you put plus or minus, it doesn't matter. T to the minus 1. T is minus 1. So this is lambda. I'm sorry. Sorry, there is no T. This is lambda. I'm sorry. Eh? This is a new random variable, so I call it y. I have written x above, no, so that's why I called it y. This is a new density part. If I write f, it will be same f, no? Otherwise, I have to use g. There is nothing. X is some random variable which follows exponential. Y is another random variable which follows this. I don't want to. There is no point. It's just a different random variable. You are happy with this. This is what you want, right? Then what is this f? What is this f? People will ask. So that's why I used a y. There is no reason. Okay, you take this is one example. Okay, this is exponential. There is no x. You take this. This is a exponential random variable. If this follows this, this is a double exponential random variable. Okay. Yeah, this is another random variable which is defined like that. This is symmetric random variable. Okay, density is symmetric, so the random variable is also symmetric. From x, which is okay, you can actually define a function. I mean, invertible function from positive real line to whole real line, and using that you can get it if you want. Okay? If you want to get one random variable from the other end. So this is about normal. Okay. 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 So, okay, what is this 0 and 1? So to compute that, I want to use the, I want to, of course, introduce the notion of expectation and variance for that. Okay. So this is the definition. The definition is very similar to what we have defined for discrete random variable. So x is a continuous random variable with density f. Okay. This is not the actual original definition. The original definition has to be the random variable is defined on some probability space. Using that probability space, we have to do some integration. That's how it should be defined. But then we don't know, we haven't developed that integration. So we have to, for a continuous random variable, we can define it like that. That can be defined for any random variable, whether it is continuous or discrete or a combination of that. For discrete random variable, I defined it like that. I use the probability space to define the expectation. Then I use the probability mass function to define that. But here I can't do that because that integration we haven't developed. Okay? So I have to define it like this. Okay? This is because we haven't developed the integration with respect to general probability measures. Okay? So X is a continuous random variable with density F. Here we don't refer to the probability space where this X is defined. Only the density we need. Okay? Then we say expectation exists. I mean, X has expectation. If, I mean, which we call it as E of mod X. I mean, I will show you why we call it E of mod X, which is equal to mod X minus infinity to mod T minus infinity to T F of T dt. These are all positive, is less than infinity. Okay, it's finite. If this integral is finite, then we say the expectation exists. Okay, this has expectation or expectation exists for that. We say expectation exists for this if this is true. So in that case, when that happens, when expectation exists for X, then the expectation is defined as, that is the definition of existence of expectation. Okay, then the expectation of X is equal to minus infinity to infinity T F of T, this integral. This integral will exist if that is finite, right? So this is how the expectation is defined. Now we want to calculate this for normal distribution. Okay. Incidentally, how you don't know, you haven't, I mean, I know that double integral is not this, I mean, you people don't know about it. So I will just make some fact about double integral, because to prove that it is density, I used double integral last class. Without that, it's not possible. Okay. If you come up with some proof, you will be famous. Okay, so you will not get some $1 million prize or something, but you will certainly be very famous if you come up with a calculus proof. That is to find the integral of minus infinity to infinity e power minus x square by 2 dx. How will you find it? Using calculus, you can't do it. I mean, usual calculus, the substitution, integration by parts. You use it and come up with that. Don't ask me, can I use? You use it, try it, and come up with that. Okay? There is, you use contour integration or double integration, some sort of different method. I mean, it is just that this is not a nice function. Integral minus infinity to x e power. This is the distribution of normal. Maybe t square by 2 dt. Okay, this is equal to f of x. Okay, this is a function which is defined. This is a function, of course. This is not a familiar function. I mean, sin x, cos x, tan x, log x, these are all familiar functions. But the functions are uncountably infinite. I mean, there are so many functions. Infinitely means you can't handle that much. I mean, infinity, there are many infinity, no? Countably infinity you can handle, uncountable infinity you cannot handle. But there are much bigger infinity than this, which are called, I mean, which you will study when you do analysis 3, some Bayes theorem and other thing. So there are so many functions like that. Functions which are continuous but not differentiable at any point. Those are all functions like that. Okay, so the point is, this is a function, but you cannot. This is not some familiar function, as we know. You cannot, which you can handle with differentiation and other things. Okay, so this is of course a differentiable function, right? If this is equal to this, then if you differentiate, you are supposed to get that. But what is this function? You don't know that function. Okay, so the compute show that it is equal to 1. We have, so I will repeat what I did last time, but I will just make some of the statements. This is something about normal density. Okay, the first one, see, there is something called double integral I don't know how it, I mean, I'm sure in CMA it will be done like that, but in many colleges, people develop what is called an iterator integral and call that as double integral. Double integral is, so how will you define integral for a Riemann integration? Integral, I mean, how will you define integration? You partition and then take the limit and upper sum and lower sum and take the limit, something like that. It is not, I mean, it is I mean, it's connected to the derivative and other thing, derivative of the whatever the integral you get. That is through fundamental theorem of calculus. So that is not in, this has no meaning. Okay? Sin x is equal to minus cos x. This has no meaning unless you have the fundamental theorem of calculus. Okay? So similarly, you can do the same kind of partition if you have a surface like this, something in R2. Okay? You partition into small sets like this. Then you take the supremum and infimum over that. You take the sum. You can take any partition. I mean, you can take, there you will take interval with, I mean, some length, or you can have rectangles like that. Okay. Then you take the maximum of the, if you have a function from f from R2 to R. Okay. You want to integrate it over this area, means you partition like that and then do that. You don't need to remember that. Then you take there will be lower limit, upper limit. Then you take the limit. I mean, for any such partition, the limit will exist. I mean, it is actually what is called, instead of sequence, it's a generalization of sequence. Okay, which is indexed by the partition, and a limit should exist. Okay, so that will be the integral, double integral over this region. Okay, but that is the definition. But this you can do it by iterate. So this integral, this is written by that. So integral over some surface, yes. This is a 2 f of x dx dy. You shouldn't write dx dy. You should write as the vector dx bar, something like that, which is a vector, which you write it as dx dy, which you can over this surface, you can write it as an iterator integral. What is iterator integral? It is like partial differentiation. You partially integrate it. You have the first integration. You integrate with respect to x. Well, I mean, if the most confused thing, I mean, people get confused is how to find this limit for these two things. You have to find the limits for this. Once if you can find the limit for this, then you do the integration with respect to x first, or integration with respect to y first, or do the other way, integrate with respect to y first, integrate with respect to x first. When the function f is positive, okay, in general also there is a theorem, when f is positive, this integral s of this f dx dy is equal to the iterated integral, whichever the way you can take it. So that is the theorem called Fubini's theorem. Okay, when f is positive, you can do this. Okay, you can interchange the integral. It is Bernoulli's theorem. Sorry, this is Bernoulli's theorem. Fubini is for general function. I mean, Fubini includes both functions. So for any positive, you can do this. That is Bernoulli's theorem. Correct. Okay, that's all. So that is what we used there. Suppose this f of x, this is a function which can be a complicated function. Suppose if you can write it as some f of x g of y, then that will be just product of two integrals, right? It will be the double iterated integral will be just the product of two integrals, right? The integral f of x, integral of g of y. Okay, so that is what we use. So we want to find this. We want to find e power minus x squared by 2 dx. That's what we want to find. Okay, we want to find it. This is a positive function. Okay, so instead I find this, the square. I mean, last class I did this, I'm repeating it. We want to find this minus infinity to infinity. That's what we want to find. Okay, instead of finding this, I find the square of it. But that is same as integral of minus infinity to infinity f of x dx times integral of minus infinity to infinity f of y dy. Sorry, f of x is e power minus x square. Okay, e power minus y square by 2. Okay, y square by 2. Okay, so now this is same as the iterated integral minus infinity to infinity minus infinity to infinity e power minus x square plus y square by 2 dx dy, which is same as integrating this two variable function on whole of R2. And R2 you can have, this is x and y are one way of doing it, but this is a general, so that is equal to You want integral over R2 of this e power minus x square, this function by 2. This function you are integrated over R2, okay, with dx bar, whatever. Okay. That is that integral iterated function. But now, I mean, there is no one coordinate for R2, right? X and Y. You can write it in polar coordinates if you want. But if you change the iterated integral from one coordinate to polar coordinate, there is a formula which will be proved later. Okay, for you in the for next year in the first course in calculus, right? And not analysis 3, the other course in calculus. Yeah, multivariable calculus, you will be proven this theorem. Okay, which says that if you have some function phi of R2 to R2, of course, which is a 1-1 bijection from here, which is a polar coordinate, is something like that. X equal to R cos theta, Y equal to R sin theta. Then you compute what is called a Jacobian, which is just, if you can have any function. I mean, x equal to some function of r and theta, y is some function of r and theta, or some other variable, two variable. Then you have to have this dou x by dou r, dou x by dou theta maybe first, dou x by dou r. This is the partial differentiation. Then dou by dou theta. You compute this. This is the theorem. I'm not proving. I'm just informing you. Okay, dou by dou r. You take this matrix and calculate the determinant of this, okay, modulus of the determinant of that. Okay, then so this is what is this. Okay, this is the modulus of the determinant of this. Okay, determinant of this. Okay, then this integration is same as you just write this function, whatever that function, you can convert into f of r theta. I mean, you substitute x equal to r cos theta, y equal to r sin theta, you get a new thing, and then there is the mod j dr d theta. Okay, this is the theorem. Okay, because without this we cannot prove that that's a density function. Okay, there is no other way. So you have to this will be proven later, but we have to use this. Okay, so now let us compute this for this function. Our coordinates are x equal to, I mean, our polar coordinates, x is cos theta, y is r sin theta. Okay, you can do this, you can compute this Jacobian, it will be r, right? It will be, shall I do the computation? You can compute it. Okay, minus r sin theta, then this is sin theta, this is r cos theta, or this is just cos theta, right? No, this is sin theta. That is cos theta, sorry. Is that right? Yeah, that is cos theta. If you differentiate with respect to r, you get cos theta, this is sin theta. So, which is just you get r, I mean sin square theta plus, and you get a minus, so modulus of determinant of this. You want to find the determinant of this, modulus of this, and that will be r. Okay, so it will be like dx dy will be r dr d theta. Now let us just substitute in this, okay, which says that this iterated integral minus infinity to infinity minus infinity to infinity e power minus x square plus y square by 2 dx dy is same as integral, but then this is polar coordinates. Okay, this is r will go from 0 to infinity and the angle will be 0 to 2 pi. Okay, so it will be 0 to 2 pi, 0 to infinity, okay, e power minus r square by 2 r dr d theta. Okay, there is no theta in this. If you integrate it, you just get 2 pi. Integrating constant function. If you integrate with respect to theta, you get this 2 pi. There is no theta in this as a function, only r is there. So that is equal to 2 pi into integral 0 to infinity r e power minus r square by 2 dr. So this you know how to do it, which is just 1, right? You substitute r square by 2 equal to something, then get something. You substitute it and then you get 1. So this is 2. So this is the square of that. So this implies minus infinity to infinity e power minus x square by 2 equal to square root of 2 pi. So if you take here, so the density is 1. This is how we should prove. We prove that this is a density. Since we are discussing double integral, we will not discuss again. I will prove some other theorem using double integral, and then we will not use this. I mean, I will not ask this in exam, but I will just prove it for you. Okay. Maybe I will ask, but you can leave it in choice. Okay. There will be a lot of choice. No, somebody else can write. Okay. Okay. Yeah. So. Okay. So, I mean, since we freshly remember, just now I have done double integral, I prove this. Okay. See, if you remember, we proved the following for discrete random variable. If x is a discrete random variable, then Ex is equal to summation. X is an integer value, sorry, positive integer random variable. Okay. It's a positive integer random variable. Then this is equal to probability of x greater than or equal to n equal to 1 to infinity. If it's 0 to infinity or 1 to infinity. If you have 0, it's say it again. It was in the quiz again. Oh, it was in the quiz also. Oh, they didn't realize that it was proved in the class. It's all of you did it. Okay. 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 So we want to prove the continuous version of this. Okay. I will tell them not to ask in the quiz. Okay. So, so this is the proposition we want to prove. But as you see, as you know, the proof of the discrete one involved double summation, right? So we will use double integral here to prove the same thing. That's all. Okay. So x is a continuous random variable with density, some density with density f. Okay. And expectation exists. It's a positive value. I'm sorry. We have to write positive value. X is a positive continuous random variable. Okay. X is a positive continuous random variable with density fx, and the expectation exists. Okay. Then, I mean, you don't need to worry about expectation exists. It's just not needed because it's positive, right? You don't need to say that. This is the expectation. If this is finite, there's expectation exists. The expectation exists, I don't need to write. Yeah. Then E of x, which is same as E of mod x, equal to integral of 0 to infinity 1 minus f of x. Okay. Okay. Same as that. If you want, this is precisely integral 0 to infinity probability of x greater than x or greater than or equal to x, doesn't matter. Okay. Same as this. This is the continuous version of that tail theorem we proved for discrete one. Okay. Of course, it will involve double integral. Okay. So proof. So we want to compute this, and we want to prove, we want to consider this integral. We want to prove that this is same as this, which is this. By definition, we want to prove that. By definition, p of x equal to integral 0 to infinity x f of x dx, right? We want to prove that these two are same. That's what we want to prove. Okay. If you, but I have to convince you by diagram. I mean, there is no other way. I mean, that's how double integrals are calculated, right? You have to. Okay. So, I mean, there is no rigorous way of proving it, counting or something. Okay. You have to get convinced. Okay. So, we want to compute this integral 0 to infinity 1 minus f of x dx. Okay. That is equal to integral 0 to infinity. There is another integral again. Integral 1 minus f of x is just the integral. This is this integral, right? 1 minus f of x is probability of x greater than or equal to x, which is this between x to infinity, right? Okay. This is okay. 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 Now we want to, this is so let's see where this is integrated, the region where this is integrated. Okay. So this is the axis, this is x-axis. Okay. And this is t-axis. We have used the, I mean, we could have used y, but we are using t. Okay, this is the t-axis, right? Then this t varies between x to infinity. X varies between 0 to infinity. Okay, x equal to t is this line, right? Okay, this integration is done in this area, in this area. Okay, this what is this called? X t varies, t is greater than or equal to x, less than infinity. X is greater than 0, less than infinity. This region is this engine, right? T equal to x is, you just consider this line, t equal to x. On the other side is this, and they are all positive supposed to be, so it is this region. Okay, this region means infinite region. It is that region where the integration is being done. Okay, now you tell me, if you interchange the integral, where will the x and t vary? If you interchange the integral, t will vary, I mean, t is varying between x to infinity. If you interchange the integral, x will vary from 0 to t. X, I mean, the inside 0 to t. T will vary from 0 to infinity. Right? That's also the same thing, right? This region, I am just saying, these two regions are same. You just write this. I mean, all those xt, x is first, no? X is, t is greater than x is greater than 0. I mean, till infinity, of course. Till infinity. Okay? This is same as xt with t. I mean, x is less than or equal to t, greater than or equal to 0. T is less than, t is infinity, 0. Okay. Okay. I mean, t is greater than x. I am just saying x is less than t. Same thing. Okay. So this implies that double integral, that whatever the double integral, so that integral 0 to infinity 1 minus f of x dx is going to be integral 0 to infinity 0 to t. Okay. Then the same thing, whatever is inside. What is inside? F of t dt. Okay. Then dx, dx dt. Okay. This is integral is with respect to the t is above. This integral is with respect to x. There is no x in this. So we get just t. This is equal to integral 0 to infinity t f of t dt. This is precisely e of x. Okay. You get a t because there is no x there. You integrate this. This is constant function 1. Integrate with x, you will get just a t, integral 0 to t. So you get t. Okay. So you get it. Huh? No, you just, the interchanging is, you can integrate x first and t second, or you integrate t first and e second. For that, you have to write the limits correctly. That's all. There, the t is varying. Here, this x is varying from 0 to infinity. T is, I mean, if you consider x first, x is varying 0 to infinity. T is varying from x to infinity. Okay. But then t takes all values till infinity, right? Even though t is from x to infinity, inside that, when x is going small, t will take some all values from 0 to infinity. Now the other way, t will vary from 0 to infinity. That's clear. Where does x will vary? X will vary from x to 0 to t, right? That's all. Huh? No, f of t dt. 0 to t, x, there is no x here. Yeah. That is why you get t. There is no x in that. That's why you get t. I mean, x is with the original distribution function. Yeah. Okay. So we proved that theorem. Okay, I have some more time. Now I will just compute the expectation of normal random variable and maybe variance also. I will define variance quickly and then compute the variance also. Okay. So we'll go to that. Okay. So x follows normal 0, 1. Okay. Then we want to find the mean. Okay. Mean is clear. What is mean? E of x is equal to integral 0 to minus infinity to infinity. Huh? Say it again. Yeah, yeah. Which is the e power minus t square by 2 dt. What were you saying? You are just answering this. Ah, okay. Okay. So e power minus t square by 2. I thought you were asking something. Okay. Okay, this is the one. It's clear. What is the answer? Huh? What is the answer? 1. Huh? This without this, it's 1. Sorry, 1 by root 2 pi, I should say. Huh? Without this, it's 1. If you have t, what is the answer? No, no, I want the immediate answer. But that's why I went at y0. Y0. Odd function. Yeah, it is odd function, so it is 0. But then we have before that, but we cannot avoid it. Before that, we have to verify this, of course. That is not, then only we can do that. I mean, so we have to verify this. This is equal to, actually, we have to first verify this, then only we can do this. Okay. So for that, this is equal to this, equal to mod t e power minus x square, I mean, t square by 2 dt. For that, you have to use that formula and prove that it is finite. I mean, the positive one, it will be positive, negative one, it is minus of that. But that you can compute using that. It's clear, no? It will be 1. If you integrate between, I mean, if you do the partial integration, you need, no, you can directly by substitution, you can do. Direct substitution you can do. And that will be, I think, 2, I think. I'm not sure, but this will be finite, it's clear. This is calculus. You integrate it between 0 to infinity, minus infinity to 0 separately, where you can integrate it by usual calculus, and you get the answer which is finite. From then you can do this, which is finite. Okay, you have to verify that. So that is clear. So what we have to, so what we are worried about is, so we have to define variance. Variance of x is, I mean, we have already done this, which is, this is the mean. Okay, this is mu equal to this. This is equal to mu. Mu equal to 0. Okay. Then the variance is x minus mu whole square, which is same as e of x square minus e of x whole square. Okay, by the same thing. For that, we need expectation is linear and all that, but the integral is linear, so it's clear, right? Expectation is linear, which is clear because the integration is linear, right? Okay, so we don't need to prove all that. Okay. Okay. So, I mean, you can take it here only. We are taking the constant out. This formula, I hope it's clear. Okay. So now so this variance x for this normal, x follows normal 0, 1. Then e of x square only we have to compute, and that is equal to integral t square e power minus t square by 2 dt. Okay. How will you compute it? 1 by 2 pi is there, of course. Okay. How will you compute it? No, 1 by 2 pi missed, he said, so I will just use it. Okay. So this will be equal to, you have to use integration by parts. But then integration by parts, if you take t square, it will be t, exactly, done. So it is just 1 by root 2 pi, integral minus infinity to infinity, t and d of e power minus t square by 2 dt. You can write it like this, right? No? This is right? This is okay, no? It is this, one of the t is just minus of this, right? Yeah. Now you can integrate. I mean, this is the usual notation for the integration by parts, no? Now you get the t out and other things. Finally, answer should be 1. If you just do that, it will be 1. Okay? Compute it, it will be 1. Okay. Okay, let's stop here.
So variance
Variance is 1. So now you want to find, now you want to shift it. The usual normal distribution is the following. Okay. I mean, expectation of x1 plus x2. No. I have to prove all that. Let's. What shifted? Yeah, the shifted one. Okay. So let's just do that. So, I mean, if x follows normal 0, 1, okay, then by the same formula, the theorem we have proved, sigma x plus mu for some, I mean, it can be positive, it can be negative also, still it will work, but you have to put a mod sigma there, will follow normal, I mean, okay, let me just write it, normal mu sigma, where f of, I mean, f of sigma, mu sigma equal to 1 by square root 2 pi. If sigma is negative, also if you want to consider, you have to put mod sigma. Sigma is positive, it is just sigma. Because in the theorem we proved, I mean this change of variable formula theorem, which we proved, we had a mod there if you differentiate it. Okay? That mod sigma is coming here, and it is just e power minus x minus t or whatever, t minus mu whole square by 2 sigma square. I mean, this is what I'm using. If f is the density for x, x follows, x has the density fx, then the f of this x minus mu by sigma will be 1 by mod sigma f of x minus mu by sigma. Okay? F of sigma x plus, sorry. I mean, it should be the inverse inside. This is by the theorem we proved. Phi is the function which takes t to sigma t plus mu. Then the phi inverse will be this. Okay, that should be inside, and then we have to differentiate the phi inverse, and you have to put the mod of that. So when sigma is greater than 0, this is this. Okay, so what expectation? Yeah. Now we do expectation. So expectation is, you can take a constant out, that is clear. And if you add a something, constant random variable, then the expectation, I mean expectation, if you have a constant random variable, it's the, I mean, it's clear constant variable is not a continuous random variable. It is just one point. So we know that the expectation is exactly equal to that. I mean, actually we are mixing some sort of discrete and continuous, but that doesn't matter. It's only constant random variable we are adding. Okay. So the expectation of this will be mu if expectation of x is 0. Okay? And the variance is sigma square. We will do this again next class, okay? More rigorously. You can take sigma square. I mean, variance of ax is a square times variance of x. We will prove that, and from that we will